Thank you. Okay. Right, so hey, come on. Sitting there, I think would be easiest. Oops. How come you're right?
I was left this one.
That is terrible. Worst student ever. Okay. Do you remember what momentum is? What's momentum?
And formula?
Yeah.
It's
Yes?
mv
Yes. Very good.
minus.
No, well, yeah, you're thinking of the change in momentum, yes.
Yeah.
Is mv minus mu. Well, momentum is just mass multiplied velocity. Okay? Now, we might know what this word means if we think about our last class. What was the name of our last class? Conservation of energy. So what do you think conservation of momentum means? What about the change? Tell me. Yeah. So I'll tell you what it is. If no external force is acting, then that implies the momentum stays constant. So what does that mean? Well, it's a bit like energy, that the momentum you have at the start equals the momentum you have at the end. It doesn't change. So, I think we kind of saw this a little bit when we did our example with the rocket. So when you have your rocket, and then the gas coming out the back, at the start, the rocket is not moving. So what's its momentum? Zero. Here the rocket is moving to the right, and here the gas is moving to the left. So this momentum is a positive, and this momentum is a negative. But when they add together, they still make zero. So in other words, momentum is a bit like energy. In total, it doesn't change. And that can be very useful for certain types of problems. Just like when we saw the energy, we saw was useful. So let's do a little example. Can I go down? Yeah? Yes? Okay. So a small example. We take, like the person, remember in the video with the jetpack. So at the start, it's not moving, and then later, well, let's make it a rocket. So inside here, there's some gas, and then later the gas gets fired out. So I'll do a line down the middle here and do start. Okay. So what's the momentum of the rocket? Well, that's zero. And the momentum of the gas at the start is also zero. So the total momentum is zero. In this picture, let's say the gas goes down with velocity v. And we don't know the velocity of the rocket going up. an example. So here we have momentum of the rocket. Let's say the rocket is big M and the gas is small m, is mass multiply velocity, so that's m multiply x, and the momentum of the gas, that will be small m multiply v. So the total momentum is mx plus mv. But I said the momentum should stay the same, so that means these two should be equal. So I get mx plus mv equals 0. So I get x equals minus mv over m. So look at this little result that we have. If we make the gas go faster, if the gas is going faster, then what happens to the speed of the rocket? It's going faster too. If there's more gas that comes out, then what happens to the speed of the rocket? It goes faster. If I make the rocket's mass bigger, what happens? It's slower. And if I make the rocket's mass smaller, faster. And this is all what you expect to happen anyways. Okay? So this is the basic idea of conservation momentum. And we will do an example now of it. Okay? An example with numbers. Yeah. Oh no, this can be for anything. So in my next example I will do, we can see that. Yeah. Okay, can I go down? Yeah. So yes? Yeah, okay. So let's take an example of using this. And the most common place to use this is in collisions. Collisions mean things that come together and they crash. So we'll have a simple little example here. Car, and then a big truck. It's a truck, trust me. Not even close. Oh, you know what a truck looks like. There. So let's say the truck has mass 30,000 kilograms. And we'll say the car 2,000 kilograms. Okay, so we'll say that the car is moving with a speed of, how fast will we make it? 30 meters per second maybe? Maybe that's a bit too fast. 25 meters per second. And the truck is not moving, it's at rest. Okay, we're happy with the type of problem I'm doing here, yeah? Now what will happen is the car will crash into the truck, so afterwards you have this. You get what I've done here. They've come stuck together. So they're now like one object. So what will be the mass of this object? Well, that's just going to be 32,000 kilograms, isn't it?
Yeah.
So what we can do is we can work out how fast this is going. Because you know, if this car crashes into this truck, it's going to make it move forward. Who could this be? We've got everybody, don't we? No, wrong room. What was I saying? Oh yeah. So we know if the car crashes into the truck moves forwards. And we'd like to know how fast it moves, okay? So we can use our momentum. At the start, we have momentum of the car, which is, no, not the car isn't zero, the truck is zero. Yeah. The momentum of the car plus the momentum of the truck equals the momentum, and then afterwards, at the end, we'll call it the momentum of the mess, the crash. Okay, what's the momentum of the car? What's its mass? 2,000. Yeah. And then its speed, 25, plus 0 equals 32,000 V. Did you get the V for me, Hugo? Or? Yeah, what's the V? The V will be 2,000 times 25 over 32,000. Well. Now, before you tell me the answer, it's good in physics to have a feel for what type of number answer you should get. So, do we think the answer should be more or less than 25? We should think it should be less than 25.
Yeah.
If we look at the situation, we have a small car and a big truck. So do we think it should be near 0 or near 25, the answer? Nearer to 0 than it should be to 25. So I'm expecting an answer between 0 and 10. So what is the answer then?
1.5.
Yes. 1.562. And it's important that you do this, because in the exam, a simple mistake would be to maybe miss a 0 on your calculator, and then your answer would be 15.62, right? You should feel like that's wrong, and you should check again. So it's good to have an idea in your mind about what the answer should be. Okay. Now, there is one condition, and I'm going to say it again if we go back to the definition, because it's important. No external force. So this doesn't work if there is a force here. And we can see that's a small problem, because usually there are forces with things, like I'm pushing this, or whatever. So usually when we deal with these problems, we imagine as if there's no force, that it's almost like a shopping trolley, or like a toy car that's just rolling. But it's still going to, even if there was a force, it's still going to be roughly this number. So it's still useful anyways. Now, the next part, what I would like people to do for me now is to tell me the kinetic energy of the car before the crash, the kinetic energy of the truck before the crash, and then the kinetic energy of this combination after the crash. So once you have it, I'll write it down here. Kinetic energy of the car before, kinetic energy of the truck before, and then kinetic energy of the crash after. You shouldn't really be looking, you should know how to do it. So I'll wait for you to give me the numbers. Yeah? Okay, wow, this one is easy. What's this one?
625,000.
And then this one?
39,062 pounds, or
39,060
39,000.
and 62?
Yeah.
Yeah, okay. So 63 then.
Yeah.
Now if we look at this picture here, the truck and the car are on the ground, so there's no potential energy. The only energy is kinetic. So what's the energy before the crash? That is 625,000 plus 0. And what's the energy after the crash? 39,063. Now this seems a bit odd because last class I told you the energy, sorry, I'm adding too many numbers there. Last class I told you the energy should be the same. So look what's happened here. The energy seems like it's less, doesn't it? Now what's happened is, if I go up, there's actually heat energy here as well. And what's happened is this kinetic energy is smaller because some of the energy is now heat. So really we should say 625,000 equals 39,063 plus the energy in the form of heat. So we can work out how much heat energy is in the crash afterwards, because you know, you can picture that after two cars crash you might see some smoke, the cars will be warmer. This is energy that was taken from the kinetic energy. But it still gives us an important result here, that the kinetic energy before is less than the kinetic energy after. And when that happens, this has a special name. We say the collision. Now, did I give you a question about this? Yes, it's number 2. Okay. When this happens, we say the collision, sorry, you might not know this word, that's the name for when two things come together. We say the collision is elastic. Elastic. Yeah, elastic means, well, it means this, that if you lose kinetic energy, sorry, let me write that again, to make it clearer, is inelastic. Inelastic, sorry, not elastic. Inelastic. So, yes, Louise, what I say? Yeah, collision means when two things come together, and then inelastic means the kinetic energy. Oh my goodness, I'm so tired, I have this backwards. It means the kinetic energy is reduced, decreased. So at the start you have this much kinetic energy, and then later you have this much, which is smaller. When the kinetic energy decreases, we say it is inelastic. So it's just vocabulary. If it's inelastic, it decreases. And if the kinetic energy doesn't change, what do you think that's called? So if the kinetic energy is the same at the start and at the end, before and after, do you want to have a guess at what the word is for this?
Elastic.
Say clearly, yes?
Elastic.
Elastic, yes. If it doesn't change. Oh, yes. Hey, you are so in the wrong room. Don't you like biology?
Yeah.
In like D207? Check your timetable.
D2 and 3.
D2 on 3. You couldn't be more in the wrong room. What was I saying? Oh yes, so we'll go back to the main question now. Are we happy with this vocabulary? Yeah, okay. So let's go back to our example here of the truck and the car. So afterwards they come together and they're 32,000. What was its speed? What did we say was 1.56 meters per second. Now will this continue at 1.56? No. What will happen? It will slow down and then eventually it will stop. So why is it stopping? What's making it stop?
The truck?
Yeah, well what exactly?
The mass?
No, not quite this.
Losing energy is good.
Yeah, but why? Why? Well, because you imagine that the wheels are locked, so they're not turning. Because if the truck is stopped, maybe the driver has the brake on, something like this. So these wheels aren't turning, they're sliding. So there's friction here. There is a force that's trying to slow it down. Because, I don't have any wheel. If we if we look here, it's okay. So this is going to keep moving, okay? But if you have the brake on, then it's going to slide and slow down, okay? So the force that makes it slow down, I think you gave me the name. Does anyone else know the name? This force here is called friction. It's the force you get when you rub your hands together. Oh yeah, I'll show you friction actually. Have you got like an English book or some book or something? Like a textbook, a school book? I need 2 books. More like a book.
Not like a book.
Yes. This will do nicely. Make sure there's nothing important in it. Do you need to keep this? Alright. So I'll show you friction. The force you get when 2 things rub. Okay? You know? Now, some of you know this and some of you don't. And some of you are thinking, what is he doing? He's gone crazy. I should have given you something to do while I'm doing this. Okay, I'll try and go faster. Skip some pages, oh well. Should still work. Oops. Okay, I didn't quite get every page, but I'm hoping it'll work. Yeah. So all I did, you saw that there, I just put the pages on top of each other, right? So, Louise, give your hand, hold one hand there. Okay, other hand here. Okay, and pull apart. Pull. Come on. Oh, maybe you're not strong. Okay, we'll try someone who's stronger. Here, you try now. Go on. Come on. What's wrong with you? Oh, you're so weak. No. Go on, try. Don't break it.
Yeah.
Oh, don't tear it. Try. Pull. No. And you get the idea, okay? You can do this at home.
Yeah.
So what force is keeping it together? What is the force that's keeping this together? It's friction. That's what's keeping it together, okay? So friction, when you rub things, can be a strong force. Now, how to separate? So, to separate...
So sometimes the floor is smooth.
Yes, if the floor is smooth, then there's no friction. Yeah.
But how to unload the floor is smooth?
The question will tell you.
The question will tell you, yes, yeah. Not there. Hold on. Don't want to do it one by one. Uh-oh. Oh no, this is separate, it's okay.
Everyone balances.
Still, even though it's less pages, it's still quite strong. Oh, not enough.
I don't know if this is mine.
What's there? I'll have to get you a new one. That wasn't supposed to happen. Whose was that?
Who?
Oh, it's okay, I don't like you. So. Oh, I'm so sorry. Physics experiments gone wrong. Oh dear, oh dear, oh dear. Oh, this is terrible, terrible. I know what I'll do. We'll take this out, and then I can get a new one. Like your maths one. You got your maths one? Give me your maths one. Yeah. No, your maths workbook. Yes. Good. So later today in maths class, I'll give you another one of these. Yes. There now.
Okay.
All fixed. So later today, I'll give you another one, okay? All right. Oops. Okay. So friction is the force that slows it down. Okay, so small problem here. I'll tell you that the S is, let's say, 10 meters. So what happens is the truck and the car hit together, and then they slide for 10 meters and stop. So I want everybody to calculate the acceleration for me, the A. I want to know what the A is here. Yeah, let's write down UVATS. So what's U? 1.56. V? 0. A, we don't know. T, we don't know. S, 10. So what formula? V squared? Yeah, V squared equals U squared plus 2AS. 0 squared equals 1.56 squared plus 20S. Sorry, 20A. So what's the A? Who?
0.12168.
0.12168, so 7 then. And it's a minus.
Yeah, just Irish.
Yeah, and the reason for the minus is because it's going to the left. So that's the acceleration, but I would want to know the force. So what formula could I use to get the force? F equals ma just. So can you multiply this by 32,000 and we can get the force?
3,893.
Newtons. 3,893, sorry.
Yeah.
I heard 3, but I wrote 6. With a minus. So that's how much force is slowing the crash down. Nearly 4,000 newtons. Okay. Can I do another example now? Are we happy enough with that? Yeah. So I want to do an example now that uses conservation of energy and conservation of momentum. So the famous example always is this. Which one? No. Well, no, not that one. This one. Sorry. I'll draw it again. So this is 10 kilograms and it's at the end of a rope, and there's a small bullet here, let's say of, I don't know, 0.1 kilograms, and it's going 200 meters per second, and it comes along and then it crashes into the block, and then it makes the block swing up. So the question is, how high does the block swing up? Don't really need this dotted line here. Okay, do you have that drawn? So tell me, when we look at this part, the bullet colliding with the block, should we use conservation of energy or conservation of momentum? Ah no, momentum. Because we need to picture, this is a lot like the last example with the car that hits the truck. It's the same type of problem here. The bullet hits the block. So we should use conservation of momentum. So at the start, what's the momentum of the bullet? It is 0.1 multiply 200. And what's the momentum of the block? Zero. Then afterwards they come together. Its mass is now 10.1. And its velocity, we call it v. So from this you can tell me what the speed is. Can you get the v for me, please? So v equals then, spread by 2 or something?
It's 1.98. Yeah, 1.98.
Okay. Yes, 1.98, yeah?
Yeah.
Okay. Now, let's look at the second part of the process. So if you go here, from here to here, what should we use?
Conservation.
This is conservation of energy. So what type of energy does it have? So conservation of energy now. What type of energy does it have here? Kinetic, potential, what? Just kinetic. So that's a half m v squared. Can you see that okay? Yeah. Now, when it's up the top, what type of energy does it have?
Zero.
Yeah, zero velocity. It only has potential. It has no kinetic. So what's the formula for potential energy? M G H. So now you can tell me what the H is. So what do we get for H?
Isn't it just a square?
Oh, absolutely. Squared there. What's that?
2.0387. I think
2.0.
0.04.
04 will do, yes. Yeah?
No, I don't think.
No.
But you told me this!
No, I got the 0.2.
Yeah, I got it wrong.
That's okay. What you got?
0.2.
0.2. Okay, that sounds better. Yeah. I thought 2 was very big as a number. So this would swing up 20 centimeters, 20 cm. Okay, what I'm going to do next now is, let's say that this here is 1 meter. I want to know this angle. Now we'll do this more in maths class, but I'll do it anyways now. So if I draw this again, let me just draw it again here. Here is 1 meter. Here is 1 meter. This distance here is 0.2, right? Okay. So if I tell you that, this here is 0.2. How much is this? 0.8, because the total must be 1. So that's 0.8, and then that there is 1, and this here is 90. And this here is the angle we want, theta. Well, you know what? I try and make it a bit easier for you. I can't really. Sorry, no. Theta. Does anybody know cos theta? What is the formula? I haven't told you this yet, or did I tell you this? I don't remember.
Jason and Falcons.
Yeah.
0.801.
Yeah, I'm trying to think if there's an easier way to do this with you. Yes, I know. Okay, look, I'll do this now, but I'm telling you, I haven't done this with you in math class yet, so if you don't know what I'm doing, don't worry. We'll do this in math class later, okay? But for those people who do know, we can say cos theta equals adjacent over hypotenuse, yeah. So then theta equals cos inverse 0.8, which is 36.87 degrees. Now, some people have done this in high school. Maybe they remember it, maybe they don't. But if you're not so familiar with this, it's called trigonometry. That's the type of maths I'm using here. And let me show you something here now. So, I don't know, some people maybe, you would have done lots of this, are familiar with this sine, cos and tan. But if I show you here now in the maths, oh, teacher downloading twice. I just want to show you when we'll do this in maths. It's still a couple of weeks away, but if you want to brush up on it, I can show you which video to look at. Let's see, Maths Part 1. It's in the section Trigonometry, which is chapter 5. And it's this here, okay? The first lesson. If you want a little bit of revision from high school, or if you can't wait until later, you can watch this video, okay? Sine, cosine, tangent, and we all know Pythagoras. Yeah. So anyways, maybe you can just write this title of lesson down if you want to watch it later. Yeah. Pretend to write it down for me, please. Sine, cosine, tangent, and Pythagoras. Okay, let's see what else to do. There's something you have which we don't use, the Newton's law of restitution, the formula of the E. So we don't have that one, which we don't use. Okay. Did you get the name?
Yes.
Yep. Okay. Right. Do another example now. Let's see. What will I do? I want to do something weird. Let's see.
Actually, this example just how to get the tangle.
Which one? Yeah, say again. Yeah.
I mean this example
Yes.
to show us just how to find
The angle. Yeah. That's all. And this is more maths than physics, you know. So we'll have, if you look actually, if you got your maths book, you have your maths book, of course. I remember using it. Oh yes, now this one has no. Here, if you look at page 68 in maths class, we'll learn how to find angles in triangles. So we'll do this in maths class, so don't worry if you can't understand it yet, okay? But if you want, you can watch the video. Yeah. Okay, another example now. What are you doing in chemistry? What are you doing in chemistry? Don't know?
Doing something.
Doing something, I hope, yeah.
What are molecules and bonding?
Molecules and bonding, stuff like this, okay. Have you done things like mass of proton, mass of neutron?
Yeah.
Stuff like this. Mass of electron is quite small. So an isotope is the same number of protons. So the number of protons is the atomic number, but a different number of neutrons. So what were we doing? Carbon, was it?
Yeah.
Yeah?
Daisy?
Yes, it was like carbon, wasn't it? So what isotope is that? That's carbon 12 or what? I mean...
The isotope?
Yeah, for carbon that you're doing. 13, is it? Carbon 13. Yeah? C13? Yeah? How many protons does carbon have? 6. How many neutrons? It should...
7.
Yeah, for the isotope it has... Sorry, not 7 there. 13. Okay? So if I draw this... Well, I won't... Well, no, I will. 1, 2, 3, 4... I don't know. Whatever. 5, 6 protons. and then 7, 1, 2, 3, 4, I don't know, 5, 6, 7, whatever, neutrons. So let's say this is at rest. And then, for whatever reason, one of the neutrons leaves. So how many protons and neutrons do you have here now? You have 6 protons and 6 neutrons, and then one of the neutrons is moving this way. Okay? So, what speed will we give it? We'll make it very fast. How fast?
20,000.
Let me see. Pick a reasonable number.
2,000.
2,000 meters per second? Let's make it 1,000. Yeah. So this is moving away very fast at 1,000 meters per second. So my question, I want you to try this for me, is how fast will this move to the left? So I'll draw it again for you. At the start, you have 6 protons and 7 neutrons. Or if you want, 6 protons, 6 neutrons, and then 1 neutron here. And then later, you still have 6 protons, 6 neutrons, but that 1 neutron left. And its speed is 1,000 meters per second. So my question is, how fast is this going? What's its speed? I'd like you to try and do this for me, and then I'll do it. Yeah, well, you have, well, you see, this is where this calculator comes in. So, can you take out this calculator? No, you're at a disadvantage now. If you take out this calculator, and if you type Shift 7, and what does it say now on the screen? Read it to me. Constant number 1 to 40. And then if you look at your lid, if you look at number 1, what's number 1? MP. That's mass of proton. And what's number 2? Mass of neutron. So if you type in here 0, 1, and equals
1.3. Oh, that
1.67. You got 1.67?
Yeah.
That's the mass of the proton. So this is one of the reasons I recommend this calculator, because you can use it in physics, chemistry, and maths. So you can use it for all your subjects except the AP. Nothing will help you there. Whose is this? That's yours. You don't have this calculator. When will you buy it? Promise? Okay. You don't have this. You don't have this. Do you have a formula book for chemistry, or do you have the constant in your chemistry notebook?
Yeah.
Yeah, so do you have your chemistry notes? Yeah, so I'm sure Lorraine gave you the math in her notes.
Yes.
Yeah.
But we haven't like done it or anything.
Oh yeah, but you can look up to see how big it is.
Is it for the mass?
The mass of the proton and the mass of the neutron.
31.0 is for proton.
Proton? 31?
See? Carbon.
No, just proton, not carbon.
And we're looking for the actual mass.
Oh, I see. Oh, okay. You're going to give me the mass of the of this in total. Yeah, okay, that's fine. It's on the periodic table, isn't it?
I thought we were looking for the actual mass of the proton.
That's what I was going to do. Yeah. I would rather, just for now, I'd rather. Here, I'll write it on the screen. Sorry. Yeah, sorry. Shift 7. All right. Here, look. Mass of proton equals 1.67 times 10 to the minus 27 kilograms. And the mass of the neutron, it's about the same. Yeah, you can just take it to be the same. And look, this is roughly, have you done this letter, AMU? Do you know this in chemistry? Have you done AMU? No, okay, forget it then. Any answers yet? Nearly? Hey, it's snowing. Let's have a look. The problem, the ground is wet, meaning the snow won't stay. Oh well. Someone have an answer?
I get 83.5.
Yeah.
83.5 sounds about right, yeah? Because the left is 12 times bigger than the right, so I feel like the answer should be about 10 times smaller. So an answer somewhere near 100 is what I would have guessed. Yeah, something in this area. Although you got 80 something?
Yeah, 83.5.
Alright, I'll do it now. Now, I gave you the mass to proton and the mass to neutron. In fact, I didn't need to give it to you. I'm going to take a little shortcut. I'm going to call this X and X. It will end up cancelling. So I don't want to write this number because I'm tired. I'll just call it X for now. Alright. Before, what is the total momentum at the start? 0. Yes? And then afterwards, there's this momentum, which is mv, so that's 1000 x plus, and then there's this momentum, which will be 12 x's, 12 of these, yeah? Plus 12xv. Now you can see here my little trick, I can cancel the x now. So I didn't actually need to tell you this. So I get 0 equals 1000 plus 12v. So v equals minus 1000 over 12. What's that number, please? 80 something?
83. 83, yes.
Why is it minus?
The direction.
Because, yeah, direction is going to the left. Yeah. In physics and chemistry, you will learn sometimes, with isotopes, that neutrons sometimes do leave the atom, the nucleus. It does happen. And of course, when it leaves, that means that you can see here that the atom now must be moving to the left. It's a neutron left to the right. Yeah. Does anybody know what this is called? When neutrons and protons leave a nucleus of an isotope? Very good. Radiation. This is just radiation. Yeah? No. You don't know this word? That's okay. You will learn it in semester 2. Okay. Do I want to do more examples, or have I given you enough here? We won't do it right now. Well, actually, yeah, this is a little bit weird. What's the kinetic energy at the start here? 0, isn't it? And what's the kinetic energy here? Well, most importantly, it's not 0. And the kinetic energy here? Not 0. So, think back to my last lesson. Here, the energy in total is 0. And here, the energy is not 0. So what happened? We got energy. But of course, we can't make energy. So this energy came from somewhere. So something did work to give this energy. Anybody have any ideas where this energy came from? From what, yeah? What do you mean? I mean, if anybody knows, that's great. I don't expect anyone to know, but if you have an idea, tell me. So here the energy is not 0, here the energy is 0. So that means the energy came from someone. Do you remember the example of the man lifting the box? The energy came from the man. So where did the energy come from here? Any ideas?
Electric field.
Adventuresome, but no, I don't think it's complicated as this. Well, the answer is, you've done bonds with Lorraine, haven't you? So this neutron is bonded to this nucleus. This bond needs energy. When the bond breaks, this energy is freed, is released. So in other words, this energy came from the bond. Okay? So, you know, what bonding have you done? Covalent bonding? Ionic bonding? Yeah. So this bond is a force. And when this is broken, it releases the energy. You think about like a spring. You know, if you have a spring and you push the spring together, you know, and then if it breaks or something, it can release the energy. Okay? So I'm saying that energy came from the bond that kept it together. The bond broke and the energy was released. Yeah? So what I'm trying to do is I'm trying to relate your physics to your chemistry and trying to relate this to the previous lesson. So we're building up in layers. Okay? Now I have some questions for you to do. There are 4 questions, but as you can see, these questions are big questions because they go in steps. But I think if we finish at 10:40, yes, you should have enough time to finish these now. And again, if you don't finish them, they can be for homework. And whatever questions you can't do, we'll do them tomorrow. I'll do them tomorrow in the tutorial. Okay? So I think you all got this page, except this is yours, is it? Or this is yours, yes, okay. So if you can try to do, on the last page, Saeed, yeah, if you can try to do those 4. So the first example is like the one I did with the car and the truck. So that should be okay for you.